Hi guys, welcome to Control Engineering, and this is our third video and we are looking at transfer function. It is not the first time that we are hearing about transfer function, and we have heard it in the first video introduction to Control Engineering and also in Laplace transform. As usual, Engineer Motion Marfu is my name, and for any communication, Motion Marfu60@gmail.com or via WhatsApp +26371753586. Guys, let us enjoy transfer engineering, and according to me, this is where control engineering begins. Let us go. Introduction to transfer function, and we are saying a transfer function of a control system is an S-domain expression. You remember your Laplace transform where we were talking of the parameter S, and it simply describes the relationship between the output and input variables of the control system, and the assumption is initial conditions are zero. Loosely, we can simply say it refers to gain because we are talking of the ratio of output to input. But strictly speaking, we will be talking of the Laplace transform of the output, the ratio of the Laplace transform of the output to the Laplace transform of the input. And we are saying any physical system is mathematically described, as we saw even in the two previous lectures, by a set of linear differential equations, and these are known as system equations. To solve these system equations, it is easier and simpler to use Laplace transformation, as we saw. And we are saying we assume initial conditions to be zero. Normally, we take initial conditions to be zero as in actual analysis or when we are designing control systems. And what do we mean when we are saying initial conditions are at zero? We are saying if they are capacitors, if they are inductors, they are not storing any energy. This simplify the equations to determine the ratio of Laplace transform of the system output to the Laplace transform of the system input. So we'll be able to investigate the properties of a particular control system. This ratio is what we call the Laplace transform. Transfer function definition, and we are saying it is the ratio of the Laplace transform of the output response. Normally we designate it as C of S to the Laplace transform of input, and we said this input is also known as the stimulus or the excitation, and we are saying the assumption is all initial conditions are zero. This is a control system in time domain, and this is a control system in S domain or in Laplace domain, and we are saying the input is R of t, the output is C of t, and this is the gain of the system. If we find the transfer function of this, we are going to find the Laplace transform of R of t, and this is R of S, the Laplace transform of the gain, which is G of S, and the Laplace transform of the output, which is C of S. So we are saying this parameter is what we call the transfer function. This G stands for gain, and we are saying this is the Laplace transform of the output C of S divided by the Laplace transform of the input, which is R of S, and the assumption is all initial conditions. Impulse response. You remember our look at this standard test signal in Laplace transform. We are now revisiting it, and we are saying impulse response and the transfer function, and it has been proved that the Laplace transform of an impulse function is 1. It is equal to unity, and we saw that the Laplace transform G of S is equal to C of S. This is our the Laplace transform of the output to the Laplace transform of the input. Hence, we can safely say C of S is equal to the Laplace the transfer function multiplied by the Laplace transform of the input. So we are saying the output C of S can be found in terms of the transfer function G of S, and hence G of S and R of S are Laplace transforms of G of t and R of t respectively. This we know. Therefore, the response of the input can be found at t is equals to 0. This equation represents a general equation and it is valid for any input. Let us take the impulse input. We are saying our input there is an impulse signal, and we are saying R of S is equal to Laplace transform of the impulse signal, which is delta t, and we know that it is equal to 1. So we can safely say the Laplace transform of the output C of S, which is this term, is equal to G of S. Why? Because the Laplace transform of the input, because it is an impulse signal, is equal to 1. Since this is equal to 1, and please take note that the inverse Laplace transform of this is equal to G of t. We are talking of Laplace transform pairs, and this equation suggests that for any impulse input to a system, the impulse response, this is equal to the transfer function G of S. We'll be revisiting more often these standard test input signals when the properties of a transfer function, and we are saying the ratio of the Laplace transform of output to input with all conditions equal to 0 is known as the transfer of a control system or of a system. Number 2, the transfer function of a system is the Laplace transform of its impulse response under assumption of 0 initial conditions. Take note of this. And we are saying if we replace S variable with the linear operation d is equals to d dt in a transfer function of a system, we can find the differential equation of the system. The transfer function of a system does not depend on the inputs to the system. You will see this, and the system poles and zeros. You will be revisiting this, guys. You remember in mathematics, pole and a zero, your Z transform, your digital signal processing, and we are saying the system poles and zeros can be determined from the transfer function. We'll be covering this. This is the reason why I say this is where control engineering begins. Take note of the stability. I said, who doesn't need a stable relationship? And we are saying stability can be found from the characteristic equation. Very soon we'll be defining what a characteristic equation is. And we are saying that the transfer function cannot be defined for non-linear systems. It can be defined only for linear systems. Guys, I think now you must be beginning to appreciate control engineering. If you have started to do advantages of a transfer function. Transfer function, it is a mathematical model and it gives the gain of the system. Remember your gain, ratio of the output to the input. Since Laplace transform is used, the terms are simple algebraic expression. It is easier to solve algebraic expressions since we are not using differential terms. But 3, if a transfer function of a system is known, the response of the system to any input can be determined very easily. We are going to experience this. Poles and zeros of a system can be determined from the transfer function. Poles and zeros of a system determine the stability of the system, especially their location. Then the last but not least, the transfer functions help in the study of stability and analysis of control systems. So we'll be looking at disadvantages of transfer functions. Transfer functions can be defined only for linear systems, and number 2, initial conditions lose their importance since transfer functions do not take into account the initial condition. And we are saying no inferences can be drawn about the physical structure of any system from the transfer function. It will become clearer if or when we look at or when we solve some problems. So another worked example, and the question goes, find the transfer function of a system if its impulse response is e to the power minus 3t. And we are going to look at the solution. So we are now going to find the Laplace transform of the system, and we are saying this is the Laplace transform of e to the power minus 3t. And guys, we know that the Laplace transform of this equation is equal to 1 divided by s plus 3. This was the reason why we looked at Laplace transform before transfer functions. And we are saying since the impulse response of a system gives its transfer function, we can write You remember, let me go back. You remember G of S is equal to C of S times R of S. And we are saying in this case, our R of S is equal to 1. Hence, the transfer function is equal to G of S, and this is equal to 1 divided by S plus 3, because we know that our R of S is equal to 1. Another question, if the transfer function of a system and applied input to each are 3e to the power minus 3t and e to the power minus 4t, find the response of the system. We know the response of the system is, the Laplace transform of the response of the system is C of S, but in this case we are finding the inverse of that, and we are now proceeding. G of t is equal to this, and the Laplace transform of this is equal to this. We have calculated it from the above question, and we are now given the reference input is equal to e to the power minus 4t, and we are given it there. So we are saying the Laplace transform of the input is equal to this. How do we find the Laplace transform of the output? This is equal to Laplace transform of G of t multiplied by the Laplace transform of R of t, which is this. So how do we calculate the response C of S? This is our solution. C of S is equal to G of S multiplied by R of S, G of S multiplied by R of S. We are now going to, guys, what are we going to do? Using partial fraction, if we express this in partial fraction form, it is going to be this. And if we take the inverse Laplace transform, then we are going to find the response of the system in time domain. And this is the expression. Let me correct that statement. It's now correct. So guys, take notes. Actually, let me emphasize the following important points. The Laplace transform of this is equal to this, and this is the Laplace transform of the output. G of t is Laplace transform is G of S. R of t is Laplace transform is R of S, and this is the. We are now going deeper and deeper, this time poles and zeros of a transfer function, and we are going to start with defining the two polynomials. And we are saying the transfer function G of S, the transfer function G of S is equal to the response of the system C of S divided by the reference input R of S, where these two terms are polynomials in S. And we are saying we are now going to let C of S be this polynomial and R of S be this polynomial. So the transfer function can be written as this polynomial divided by this polynomial, and this can also be written as this. And we are saying our K is the gain. Zeros of a function are defined as the values of S for which the magnitude of the transfer function becomes 0. What do we mean? We are saying if the numerator of the transfer function is equated to 0, then we'll be able to find the zeros of a transfer function. And take note of this description of zeros, and we are saying if the zeros of a transfer function are not repeated, then we call that a simple zero. But if they are repeated, they are called multiple zeros. What do you mean by the pole of a transfer function? This is the value of S for which the magnitude of the transfer function becomes infinity. What do we mean? We are saying the denominator of the transfer function must be equated to 0 for this to be infinity. So we are saying if the pole of a transfer function is not repeated, we call that a simple pole. But if it is what actually is the pole of a transfer function? We now understand what a transfer function is. We have got a numerator polynomial as well as a denominator polynomial, and we are saying the pole is the root of the solution of the characteristic equation, and it is obtained by setting the denominator polynomial of the transfer function to 0. And the value of S that makes the transfer function approach infinity is what we call the pole of a transfer function. We are simply making the denominator equal to 0 for it to approach infinity. And we are saying for a complex pole, we are saying a complex pole always appears as a complex conjugate pair. Please take note. And what is the zero of a transfer function? The zero is the root or the solution of the equation, and it is obtained by setting the numerator polynomial of the transfer function to 0. And we are saying the value of s that makes the transfer function equal to 0 is what we call the zero of a transfer function. Let's see, it will become clear. Worked example, determine the poles and zeros of the given transfer function s plus 1 divided by s in brackets s plus 5. We will start with this. We'll be looking at the denominator. So we are going to say s in brackets s plus 5 is equal to 0. So for that to be equal to 0, it's either s has to be 0 or s plus 5 must be equal to 0. So this means that our s is equal to 0 and s is equal to minus 5. You are done insofar as calculating the poles is concerned. The transfer function approaches infinity when s is equal to 0 or s is equal to minus 5. In other words, this will approach 0. So there are two poles of the transfer function, s is equal to 0 and s is equal to minus 5. And these are the solutions to the characteristic equation. And the characteristic equation is s in brackets s plus 5 is equal to 0. This is our characteristic equation. Some questions can require you to form a characteristic equation. Clearly, there are two roots of this equation. Zeros, s plus 1 is equal to 0. So s is equal to minus 1. So the numerator of the transfer function becomes 0 when s is equal to minus 1, setting the value of the transfer function to 0 as well. Thus there is 1 in brackets finity 0 at s is equal to minus 1. Please take note, we are done. S is equal to minus 1 is our 0 and s is equal to 0 and also s is equal to minus 5. So we have got two poles. What is the significance of this concept? It is going to become clear when we have a look at root locus. It's a separate topic that we are going to have a look at in one of our lectures. So the root locus shows the path that is traversed by the poles of the control system. The location of these plays an important role in the performance of our system. So don't worry. We're now going to have a look at the characteristic equation, and we are saying the denominator polynomial in terms of s of a transfer function is what we call the characteristic polynomial, and when we equate it to 0 or when we set it to 0, rather, it is now called a characteristic equation as shown. S to the power n plus an minus 1 multiplied by s to the power n minus 1 plus blah 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 an. This is what we call the characteristic polynomial, and when we set it to 0, we call it a characteristic equation, and we've got a question to that effect. And this is our transfer function, and we are saying we are now going to find the poles of this transfer function, and we are going to set this equal to 0. It becomes a characteristic equation, and we are saying poles are at, if we set this equal to 0, it's either s plus 6 is equal to 0, therefore our s is equal to minus 6 for that to be equal to 0, and also our s plus 4, if we equate it to 0, it means that our s will be equal to minus 4. So we have got poles at s is equal to minus 6, and we call this a simple pole, but at s is equal to minus 4, we have got multiple poles, and we call that they are of order 2. That is, it has got a second order multiplicity. Let's have a look at 0. At 0, if we equate the numerator polynomial to 0, we have got s is equal to minus 2. If this is equal to minus 2, then our numerator becomes equal to 0, or s is equal to minus 0.25. So 0 at s is equal to minus 2 is simple because we have got only one 0, but at s is equal to minus 2, we have got multiple zeros of the order 3. Please take note of our numerator, our power, our indice. So we are saying because of this, it has got a third order multiplicity. So it is not difficult to find poles and zeros of a transfer function. Guys, more on characteristic equation. You know your quadratic equation. You guys, you are L4 graduates, and we are saying the characteristic equation of a system is given here. And we are saying the question goes, identify the poles of the system. And how do we identify the poles? We have equated it to 0, we have set it to 0, and minus b plus or negative the square root of b squared, which is 4 squared, minus 4ac. And s is equals to 2 plus this, and also its complex conjugate. We saw this, and the poles are complex and appear as a complex conjugate pair. This is simple, no need to waste time. Let us proceed. And please don't forget to subscribe if you are enjoying or if you are learning something. More on characteristic equation. Determine the poles and zeros of the closed loop system. You remember closed loop system in our introductory topic, and this time we've got two gains, G1 and G2, and these are their transfer functions, and G1 is equal to this, G2 is equal to this, and we'll start by having a look at zeros. The numerator of the transfer function is already in factored form, and the zeros can be directly obtained. The two zeros are, if you equate this to 0, it will be 0, 1, s plus 1, we are going to equate to 0, and also s plus 1, we are going to equate to 0. Thus, we've got a 0, 8 minus 10, and also 8 minus 1. And also for the poles, they can be determined from the characteristic equation, and we'll be looking at the denominator, and we are going to multiply the 2 and equate it to 0. This is going to be our product, or our new characteristic equation after multiplying the 2. Let us proceed to the next slide and see what our poles are. Guys, we've studied engineering mathematics to the highest level. If you solve that trig function, these are going to be your poles. Please take note of the complex conjugate. This, and also your s can come to this. Guys, you remember your Gantt diagram when you did your complex numbers. We're now going to look at S-plane and pole and zero map. An S-plane is simply a pole and zero map. And we are saying, what's an S-plane? An S-plane is a special complex plane used to plot the poles and zeros of a transfer function. The poles locations on the place plane indicates the transient performance of the system. You remember your transients? The imaginary axis component relates to the natural frequency of oscillation. Don't worry about this. The pole and zero map. This is a pole and zero map is an S-plane diagram showing the location of poles and zeros of a transfer function. Let's proceed and see what an S-map is like. S-plane and zero map. This is our S-plane. We've got the complex quantity and the real quantity, j omega and the sigma. Please, this is where we are going to plot our poles and the zeros in the S-plane. Question for you: draw the pole zero map of a unit gain closed loop system given below. And this is g of s is equals to, this is our numerator polynomial s plus 1. So to get these zeros, you simply go s plus 1 is equal to 0. Then you locate your pole on the S-plane. To find the poles, s squared plus 2s plus 10 is equal to 0. Guys, you know your quadratic equation, and you produce the pole zero map of the closed loop system. Pole location and the transient response. Please take note that the location of the poles, the pole location determines the way how a system responds. So we are saying the location of a pole on an S-plane specifies the type of response contributed by that particular pole, and there's a relationship between the order and the number of poles present. What do we mean by order? This is the highest power of the S term of a characteristic equation. We are saying a first order characteristic equation is got a one pole, a second order is got two terms, etc., and we are saying they can be real or they can be a complex conjugate pair. So we'll be talking of distinct poles. A distinct pole is no imaginary pole, and it always lies on the real axis. Remember, real and complex. We are now going to look at the location of the poles on the S-plane, and we are starting with the poles on the left-hand side of an S-plane. In other words, we are starting to analyze the stability of a control system. We are saying a unit impulse input results in an output that exponentially decays to 0 what are we saying? When it is potentially decayed to zero, it means that we now have achieved this stable operation. A step input results in an output that exponentially settles to a finite value, and if that happens, we have reached the stable operation. The distance from the origin is related to the inverse of the time constant. Don't worry, we'll be revisiting time constant. When you remember tau, a pole far away from the origin has a small time constant. A pole closer to the origin has a large time constant, and it is known as a dominant pole. Take note of this point. We'll be revisiting it in more detail in slides ahead and also in lectures ahead. What about for poles that are located on the right hand side of an AC plane? They are staying for a step input results in an output with a continuous exponential rise. And once this occurs, it means that there is instability. In other words, we are saying there is unstable operation. So guys, take note, a control system, normally for stable operation, pole location must be on the left hand side of the plane. Otherwise, if it is on the right hand side, we will approach instability. And when this occurs, what are we saying? We have reached an unstable operation, whereby we have got an oscillating control system, or whereby there is a continual increase in an output, which results in the catastrophic failure of a system. The relationship between pole location and transient response. This is our imaginary and this is our real, and we are saying we've got what we call wanted response and unwanted response. For example, this is wanted response. Why? Because we've got two stages. We've got the transient stage, and after the transient stage, our control system must stabilize. And this is happening. This is also happening. It's also happening. It's also happening, and it's also happening. So as you can see, when the pole is located on the left-hand side of the S plane, we have got two we've got two responses, rather, the transient state and the steady state. But when the pole location is on the right-hand side of the S plane, as you can see, this is what we call oscillation. There's no stability. We are not reaching the stable state. It will keep on oscillating until I don't know when. And as you can see also, this response is not the wanted response. We don't have the steady state, don't have stability. As you can see, the output is keeping on increasing until the system crashes. So for the pole to be located on the imaginary axis, it's not a wanted response. Also, when the pole is located on the right hand side of the plane, the location, this is location on the zero, and this is location on the right hand side, and as you can see, the output is increasing. The output is also increasing, and this is the right hand side of the S plane. As you can also see, the output, though it is not increasing, we don't have the transient state as well as the steady state. So in future, or in slides ahead, rather, we'll be talking of the effect of locating the S plane on this point as well as on the imaginary axis, even on the negative side of the imaginary axis, the right hand side and the left hand side. This is unwanted response. This is unwanted response. As you can see, there is an exponential rise in the output signal, and this will result in the system crashing. So this is the relationship between the pole location and the transient response, and will be, when we talk of stability, guys, we'll be analyzing the location of the poles on the right hand side as well as on the left hand side as well as on the right hand side of the S plane. So this is the relationship between pole location and transient response. We'll revisit this. More on pole location and transient response. We are first going to look at complex conjugates, and we are saying complex poles can appear as complex conjugate pairs, and thus they do not lie on the real axis. And it is possible for a complex pair to have a real component of 0, and in that case both poles lie on the imaginary axis. And we are saying for poles on the left hand side of the S-plane, we are saying for a step input results in an oscillatory output, as we saw that it decays exponentially, and it settles down to a stable state or to a finite value. And what we mean by that, we are saying when it decays exponentially and finally when it settles down to a finite value, we call that stable operation. And also the distance from the origin is directly related to the natural frequency of the oscillations. We'll be looking at more of this when we do the transient response. And we are also saying the ratio of the real component to the imaginary relates to the amount of damping. We'll be looking at damping when we do the second order transient response. Also, poles closer to the imaginary axis are known as dominant poles, and with the complex poles on the imaginary axis for a 0 real component, a step input results in an oscillatory output that neither decays nor rises. We saw that in the previous slide, and if we can revisit, this is what we mean. It neither rises nor decays. This is rising. If a pole is located on the right-hand side, a step input results in an oscillator output that does not decay, but it continues to rise, and this is what we call unstable operation. You've got a question, guys. Determine the characteristic equation. How do you determine the characteristic equation? You must equate the denominator polynomial to 0, and how do you get to 0? If you get to 0, s plus 1 must be equal to 0, or s plus 10 must be equal to 0, or s plus 12 must be equal to 0. By so doing, you will be determining the poles of the system. How do you determine the zeros? You equate the to 0 and see if there are any zeros in that transfer function. And please take note that the location of the poles determine the type of output response. So can you do that one? And don't do that one at your own risk. We are going deeper and deeper, and we are now going to look at mathematical models of electrical systems. And what is an electrical model? This is an equation or a set of equations that describe the relationship between the input and output. What is a transfer function? Guys, we looked at the transfer function. This is an S-domain expression that describes the relationship between the input and output. So a transfer function is a mathematical model. And the mathematical model of a resistor element that describes the relationship between the current flowing through it and the voltage across it is fairly simple, and is simply a numerical constant R. For an RC circuit where it is desired to express the relationship between the voltage across it and the applied voltage E, we are going to consider it. And how is it expressed? This is expressed through a differential equation. Let us proceed. These are passive devices, resistors, capacitors, and inductors. If possible, all similar components can be lumped together as a single equivalent component for the purpose of analysis, and it is important that circuit operation remain unaffected by the lumped parameter approach. No need to waste time. A resistor. The current flowing through the resistor, i.e. in amperes, and voltage across a resistor are governed by Ohm's law. This we know, and this is the relationship. V is equals to IR. So I is equals to V over R. We want to produce a differential equation or a mathematical model. Let's proceed and see how this is represented. We want to express the relationship between the corresponding transfer functions of current versus voltage, output voltage versus input current is showing in the block. And we are saying, how do we proceed? We saw that C of S is equal to G of S times R of S. And in this case, we can also safely say I of S is equals to 1 over R multiplied by V of S. This is the relationship between the output current and the input voltage. As you can see, this is the Laplace transform of the this is the Laplace transform of the output current. This is the Laplace transform of the input voltage. So we can say Is is equal to Vs times 1 over R, showing the resistor transfer function, current versus voltage. For voltage versus current, we can simply say the Laplace transform of the output voltage Vs is equals to Is times R. We are deriving this, guys, from Cs, which is the response, is equal to G of S, which is equal to this multiplied by the reference input R of S. So, guys, we are now going deeper into the transfer function, and we are looking at mathematical models. This is the mathematical model of a resistor. Mathematical model of a capacitor. Remember your circuit theory. We are saying the current I in amperes and voltage V in volts across a capacitor are governed by the following mathematical equation. Voltage is equal to 1 over C multiplied by the integral of I dt. And we know that I is equal to C dV dt. The current flowing through the capacitor, though specifically we know that the capacitor is made up of two conductors separated by a dielectric, which is an insulator. No current flows through the dielectric, but it appears to. We are saying this depends on the capacitance and change in voltage divided by change in time. Because we've got integrals and derivatives that are involved, the Laplace transform is applied. And we are saying the Laplace transform of V is equal to V of S, and this is equal to the Laplace transform of this term is equal to 1 over C of S multiplied by the Laplace transform of this is equal to Is. Making Is the subject of the formula, we've got current is equal to V of S multiplied by C of S. So the current transfer function is shown in these two blocks, and we are saying the relationship between the input current and the output current is governed by this mathematical model or the mathematical equation, which is equal to 1 over C of S, which is equal to this. So we are saying from our previous discussions, C of S in this case equals to V of S, and 1 over Cs is equals to G of S, and I of S is equals to R of S. So we are saying C of S is equals to this multiplied by this. So we are saying V of S is equals to I of S, which is equals to this multiplied by this. So this is capacitor transfer function, voltage versus current. But for current versus voltage, this is our question. So we are saying Is is equal to V of S multiplied by C of S. This is our G of S. This is our C of S. This is equal to our G of S, and this is equal to our R of S. So we are saying this is capacitor transfer function of voltage, of current versus voltage. We are talking of mathematical modeling of electrical systems or electronic systems. Guys, take note. An inductor, we know an inductor is a passive device. It is also an electrical device, and we are now going to look at its mathematical model. And we are saying the current in amperes and voltage across an inductor L. Inductance is measured in henries. These are governed by the following mathematical equation. Voltage is governed by L I dt, and I is equals to 1 divided by L multiplied by the integral of V dt. If we apply Laplace transform to eliminate the integral sign, and derivatives gives this V of S. Please take note, the Laplace transform is a capital letter, uppercase. V of S is equals to L. The integral of this is equals to Is, and so we can safely say Is is equals to V of S divided by L of S, and the transfer functions or mathematical models are shown below. Then we are deriving this from these two equations after finding the Laplace transform of this as well as the Laplace transform of this. And we are saying, please take note of how you find the Laplace transform of any integral of also of a derivative. So we are saying I of S or V of S, which is equal to this, is equal to L of S multiplied by I of S. This is coming from this mathematical equation. And also from this, we've got output current I of S which is the current flowing through the inductor, is equal to 1 divided by L of S multiplied by V of S. Mathematical modeling. Let's proceed. We are now combining the mathematical model of the three passive components, RLC. So we have got a circuit diagram there, a switch, a resistor, a capacitor, in this case, and a battery. And according to Kirchhoff's voltage law, the battery voltage E is equal to the voltage across the resistor plus the voltage across the capacitor. And we are saying this is a series RLC circuit, and as initially we are assuming that there is no current flow in the circuit and the switch is open as shown, and at the time t is equals to 0, the switch is closed and E is applied, and we know that current will start to build up in the circuit and the capacitor is going to be charged. Eventually, or it's after time 5 tau, capacitor is fully charged and full voltage base across it, and the equation can be modeled that fully describes the capacitor voltage or current in the circuit from start to its final steady value, and the voltage across the resistor plus the voltage across the capacitor is equal to the supply voltage E. Let us put series RC circuit, when we are saying the transfer function, as we saw for R, L, and C, depends upon the desired variable, and two separate transfer functions can be developed, one for the capacitor voltage according to our circuit diagram and the other for the resistor current. We know this is our circuit diagram, one for the capacitor and another for the resistor current. So we are saying we'll start with the capacitor voltage, and we are saying because the voltage across the resistor is not a desired quantity, it needs to be replaced with a term containing a reference to the capacitor voltage. Please take note. So we are going to expand the resistor voltage in terms of current, because we know for our current has got a relationship with the capacitor voltage. So we are saying voltage across the capacitor plus IR is equal to E, where I is the current flowing through the resistor and also it is the current flowing through the capacitor. Capacitor current is the same as the current flowing through the resistor, since it is a series circuit and it is related to the capacitor voltage through this equation. I is equal to C dV dt, and if we replace the current in this equation, it is going to be capacitor voltage plus R C dV dt is equal to E, where I is equal to C dV dt. Let us proceed. If we simplify further, it's going to be the voltage across the capacitor Vc plus R times C dV dt is equal to E. This differential equation fully describes the behavior of capacitor voltage upon application of an external voltage E. In this case, we are not going to take the Laplace transform of both sides of the equation. This is simply going to become V capital letter V subscript C of S, and this other C are going to remain, and this is going to be S Vc of S as well, and we are going to factor out Vc of S. This is why it's going to remain in the bracket, and if we make this is the voltage across the capacitor Vc of S is equal to this divided by this. So we are now going to form a transfer function. We know that transfer function is the Laplace transform of the output divided by the Laplace transform of the input, in this case voltage. So our output voltage is the voltage across the capacitor, the input voltage is the supply voltage E of S, so it is going to be 1 divided by SRC plus 1. So this is a transfer function of the voltage across the capacitor as we saw. This is how we are going to represent the mathematical model for the relationship between applied voltage and the voltage across the capacitor. This is the voltage across the capacitor, the applied voltage, and this is the relationship between the input and the output. Please take note the Laplace transform of capacitor voltage. For resistor current, the transfer function related to the current in the circuit can be similarly developed, and we'll start from our original equation. This is the voltage across the resistor plus the voltage across the capacitor is equal to the supply voltage from Kirchhoff's voltage law, and here the variable of interest is the current flowing through the resistor, and we are saying the resistor voltage and the capacitor voltage are not variables of interest, and both need to be replaced with the terms that contain current, because our current is a variable of interest, and we have seen that the voltage across the capacitor is equal to 1 divided by C multiplied by the integral of I dt. Let's proceed. and we are going to substitute it in the equation. We know this is the equation for voltage, and we are coming from there. So we are saying this is the voltage across the resistor from the voltage across the capacitor give us our supply voltage, and this differential equation fully describes the current flow in this circuit from time t is equal to 0 to its state condition. When we turn on the switch, we are saying the transfer function, taking the Laplace transform on both sides of the equation, the Laplace transform of this equation and also the Laplace transform of this equation. This is going to give us, we know that the Laplace transform of this of I dt is equal to Is divided by C of S plus this one, we saw it, this is I of S multiplied by R, and this is the Laplace transform of E. We are going to factor out I of S, and make I of S the subject of the formula, and this is our mathematical model. We are now going to take the Laplace transform. And how do we take the Laplace transform? We are going to divide both sides by E of S. So we are saying the ratio of output to output current to input voltage is equal to C of S divided by 1 plus R times C of S, and this is the transfer function. Please take note, this is for an RC circuit. We'll do the same for an RL as well as for an RLC. We are rounding up using the black box or the block diagram. We are saying this is our applied voltage E of S. This is the current flowing through the resistor I of S, and the relationship between the two is represented by this transfer function C of S divided by 1 plus R times C of S. And we are saying it allows the output current, which is I of S, to be determined at any instant as a result of applied voltage as shown in this figure. I'm now going to demonstrate how you find the transfer function, and we've got this circuit diagram there, which is called input voltage, the resistor R, capacitor C, and the question goes, determine the transfer function of the figure below, where V in is our input voltage to the system and V out is the output of this system. This is our input voltage, this is our output voltage. Guys, remember your Kirchhoff's voltage law as well as Kirchhoff's current law, and we are saying let I of t, the symbol of current is capital letter I, and because this is an instantaneous current, it is represented by small letter I. So we are saying let I of t be the current in the circuit, and using Kirchhoff's voltage law, we are going to write Kirchhoff's voltage law there. And we are saying the input voltage is equal to drop across the resistor R, which is I of t times R multiplied by the voltage drop across the capacitor C, and this is found by multiplying the integral of current I of t by 1 over C, where our V out is the voltage drop across the capacitor, and it is this voltage there. So what are we going to do? We are going to take the Laplace transform of the 2y, because the transfer function is the ratio of the transfer function of the Laplace transform of the output voltage to the Laplace transform of the input voltage. In this case, it is voltage. And we are saying the Laplace transform of this term there, we simply change this to S. And we know that Laplace transform is represented by uppercase letters, hence this IS, R is going to remain. And also, if the Laplace transform of this, take note of the S parameter there. The Laplace transform of this of I of t is Is, and we know that this term there is our output voltage because it is connected across the capacitor, and we are going to make Is the subject of formula, and this formula is now going to replace Is, and we are going to factor out Is. We factored out Is there. This is going to remain in the brackets. Let's proceed to the next slide to see how we are going to find the transfer function of the circuit. We are done with RC. We are now going to look at RL series circuit, and this is our R, this is our L, and we are now going to find the transfer function. And we are saying initially there is no current flow in the circuit and the switch is open as shown, and at t is equal to 0 the switch is placed in the closed position, and our voltage, normally I prefer using a capital letter E, is applied. The current starts to increase from an initial condition of 0 amps. It eventually reaches a maximum value after overcoming the back EMF or reducing the back EMF to 0, and it remains in this steady state condition. So an equation that relates the inductor voltage or current in the circuit from start to its final steady value can be developed. Let us see how it is. We are now going to find Kirchhoff's voltage law, and we are saying equating the voltage drops in the circuit gives inductor voltage plus resistor voltage. So inductor voltage plus resistor voltage gives us the applied voltage as shown. Inductor voltage, let's see, the term VL will be retained, meaning inductor voltage, whereas VR will be changed to indicate inductor voltage. Therefore, we are going to expand. We are saying for inductor voltage, we are going we know our variable of interest, so we are going to include, or we are going to expand the VR term rather, so it's going to be VL plus IR is equals to applied voltage E. And we are saying since the resistor current is the same through the inductor and also through the resistor, we are saying inductor current is related to inductor voltage through this equation. This equation I is equals to 1 divided by L multiplied by the integral of VL dt. We are going to substitute this in this equation, and it is going to appear as this. So what are we doing? We are starting from the Kirchhoff's voltage law. We know our variable of interest because our current is the same through the inductor as well as through the resistor. So we are now there. Let's see how we are going to proceed in the next slide. We are now going to take Laplace transform of both sides, hence my emphasis on Laplace transform. Laplace transform of this is equal to Laplace transform of this. This equals to VL of S plus R of L. VL, you know something then. This equals to VL of S divided by S is equals to E of S. And if we factor out V of S, eventually our equation will be equal to this. Please take note that this is the voltage across the inductor. This is our input voltage, and we want to find Laplace transform of the output voltage divided by Laplace transform of the input voltage. So it is going to be output divided by input, VL of S divided by E of S. So this is our Laplace transform, showing the relationship between the output voltage or the voltage across the inductor and the applied voltage. So we're saying the transfer function relates the inductor voltage to the applied input voltage. We are now going to do the same for the relationship between resistor current and applied voltage, and we are saying this is our equation, and we know that inductor voltage is related to inductor current through VL is equals to L to I dt, and we are saying this is the differential equation for defining the amount of current flow in the circuit. We are saying we are going to, VL is going to be replaced by this equation. It's equals to this. It's obviously, guys, we are going to take the Laplace transform of both sides, and we know the Laplace transform of this is going to be I of S, this L of S plus R remains I of S is equals to E of S. I'm going to factor out I of S, and eventually the transfer function will be equal to 1 divided by L, which is by L of S plus R. The transfer function showing the relationship between the resistor current IS and the applied voltage ES, and this is 1 divided by Laplace transform of 1 divided by L of S plus R. So we are saying this is the series RL transfer function showing the relationship between current and applied voltage. Series RLC. We started by looking at RLC, then we went on to RL. We are now on RLC circuit, and this is our circuit RLC. And according to Kirchhoff's voltage law, the voltage across the inductor plus the voltage across the resistor plus the voltage across the capacitor give us the supply voltage E. And we know that this is the formula for finding the voltage across the inductor, the formula for finding the voltage across the capacitor, and the formula for finding the voltage across the resistor. This must give us E. Let us proceed and see how we are going to deduce the transfer function. This is the Laplace transform for the voltage across the inductor, the Laplace transform for the voltage across the capacitor, and also the Laplace transform for the voltage across the resistor. This must be equal to the Laplace transform of the applied voltage. If we factor out IH, this is what remains in the brackets. If we find the common denominator, this is going to be our numerator, and this must be equal to Laplace transform of the applied voltage. This implies that the Laplace transform of of current is equal to this divided by this multiplied by the supply voltage. We now want to find the transfer function. This is our output current, this is our applied voltage, this is going to be our our transfer function. So we are saying circuit current at any instant time can be determined through this transfer function in an RLC circuit, and this is how you represent it in control engineering. Our output current divided by the input current give us the transfer function. This means that this multiplied by this give us this. Please take note, must be able to apply any of these equations that we derived for RC, RL as well as RLC. Worked example, determine the transfer function of a series RLC circuit relating circuit current to applied voltage when subjected to an input voltage of 10 volts, and the resistor in the circuit is a 2.2 kilo ohm resistor, the capacitor 4.7 microfarads, and the inductance 1 millihenry. This is the transfer function, and we are going to put some values. This is the capacitor 4 microfarad, 1 times 10 to the power minus 3 henries, 4.7 times 10 to the power minus 6 S squared plus R. This is our C plus 1. Punch in your calculator, but this is the transfer function, amperes per voltage. And guys, this is for you. Determine the transfer function of the circuit below for output versus input voltage. Output voltage is measured across the RC filter. This is the output voltage. R2C, this is our output voltage. So determine the transfer function for output versus input voltage. Output versus input voltage.